Welcome. In this video, we are going to review the great GRF paper. So that's a paper focused on generalized neural radiance field. So typically, a vanilla NeRF model works on a per scene basis, which means that for a given scene, we get many images from that scene, usually more than 100, and then we train the NeRF model on that scene. So that's the standard setup. But here the idea is to similarly to what we will do with supervised machine learning, we'll pre-train a model on a lot of scenes, on a lot of objects, and then when we receive a new scene, when we get new images, we can apply the model directly to that scene without retraining, because the model has seen already a lot of objects, of scenes in the past. So that's very powerful, and that's also allowed to solve the issue that NeRF needs many images, because the model learns geometric prior from a lot of objects, a lot of scenes. Then at inference time, it can work with fewer images. So we can first have a look at the figure 1. So basically, we see that the model can work both with seen categories and unseen categories. So what does that mean? So for example, here we have a model, the GRF model. For now, we can consider it as a black box. We are going to open the black box in a bit and to explain how it's working. But basically, let's say we've trained the model on cars. Then that means that at inference time, we can show new cars that the model has never seen, and the model can generate new viewpoints of those cars. But it also learns for unseen categories, such as, for example, lamps. The model, even though it has never seen those kind of objects, it can generate new viewpoint because it has learned the geometric prior from other categories. So it's very powerful and very interesting. Okay, let's move on to the next page. Okay, so let's open a bit the model and understand how it's working. So like standard NeRF approach, we have the camera that is shooting a ray in the scene. We are sampling points along the ray. So I won't explain how the vanilla NeRF model is working. This content is based on my Udemy course on NeRF. I will put the link in the description if you want to learn more about NeRF. But yeah, let's come back to that. So we shoot rays in the scene. We sample points along the ray. And then for each query point, P in purple, we project them into all the input image we have on the, So for basically at inference time, we receive a few images of the scene, maybe 3, 4, 5 images. So let's say M images. And then basically we project back the query point into those images. And what we'll do in those images, we'll extract features from the images. So we will get a feature vector related to the point P, and we'll get M feature vector because we have M images. We are going to discuss how this is extracted in a moment, but as you might guess, there's a neural network, a CNN-based neural network that will extract the features. And then we will aggregate all those information and create a 3D feature vector. Well, a feature vector, but for the 3D point. And then based on that, we have an MLP that can predict the color and the density for that point. And then we can compute the volumetric rendering equation and get the color for the pixel. So yeah, all that part. Let's say that the rightmost part is it's really like a standard NeRF approach, but on the left we're adding features on those features that are extracted by neural network that are pre-trained on a lot of objects, allowed to generalize first to apply the model without retraining on a scene, to apply it on the fly, very similar to just standard machine learning, but also to work with fewer views. Okay, so yeah, let's have a look at the CNN. So basically, the CNN have two components. First, the CNN take into account the 3D position of the point P. So when we project the point P into the images, we are using its 3D coordinates, so that the CNN, although it's a 2D CNN, well, a CNN operating on 2D images, it has some information about 3D and can leverage that information. So that's the first thing. The CNN is using the position, but also we're adding a skip connection so that we can use the high-level features from the input image. So instead of just having an encoder-decoder, where the encoder would encode all the information, here using skip connection, we can keep the high-level features. And that's basically the base motivation for skip connections in UNet. They allow to keep the high-level frequencies on high-level information. Okay, so that's all the features are created, and then those features are aggregated later on. We are going to discuss about that. So once we have the features for each image, we can reproject them. Well, and then for the point P, we have a list of M with M features. Okay, so we can have a look at how they are aggregated. So basically, we take the features extracted for each image. We add to the features the position of the point. We pass that to MLP that generates new features that are position aware because they are using the 3D position of the point. And then we need to aggregate that information. What we need to be we need to do an aggregation. Why? Because M will evolve over time. We want our approach to have the ability to work with 3 images, 10 images, 100 images, and therefore we do an aggregation. So what we could do is just take the sum of all those features. We could do a mean, but here what they suggest to do is to do an attention aggregation. So basically what they're going to do, they're going to compute the weights of each feature using an attention mechanism, and then they're going to to do a weighted sum to get the 3D point features. And basically then the NeRF model, so the MLP, that predicts the color and the density of each 3D point is taking the location as input. Well, now it's no longer taking the location as input because the location is already embedded in the 3D point features, but it's taking the viewpoint as input, like a standard NeRF, and now it's taking as input the 3D features. And again, this MLP is pre-trained on a lot of scene, a lot of objects, and therefore it allows to generalize and to work on new images that have never been, on new images, on new scenes that have never been seen before. Here we have some results. So here we have some ground truth, so the expected results. There is this method, CRN, that we can see it's not working so well. It has issues. In terms of geometry, it's not so bad, but we can see that the shape, the geometry, it's not the geometry that you expect. They do not. This model has learned some categories, so it has learned cars. So it will generate a car. It generates something in its manifold, but it does not generate something that is meaningful. We can see that the shape do not agree with the expected shape, and the color do not agree as well. But we can see that GRF agrees very well with the ground truth. So that's pretty impressive. We can have a look at more results. For example, here what they do. Here we have a look at the standard scene that are used to train NeRF. So here what they do, they have the first they just test generalization. So there is 8 scenes that are used to train NeRF. For example, the Lego scene, the drum scene, the hot dog scene. So these are blender scenes. And basically what they do, they train on 4 scenes and then test on 4 other scenes. And basically here they test on that scene. So the model has never seen those scenes before, and this is what we get. So we can see that we start to guess the object. This is how it should look like. These are not the ground truth, but these are results on results that are better than the one on the left. But so we start to have something, but it's not perfect yet. Here it has been trained on only 4 scenes, so that's not a lot, as opposed to previous results where it is using the ShapeNet scene, where there are much more objects. So here basically when they train on so few scenes and then test it on the fly, results are not so great. But what they can do, they can fine-tune the model for a few epochs, only 100, 1K or 10K. And these are the results after a 10K iteration. on already after 1k iteration, results are already great. Okay, here is the ground truth. I didn't know that we had the ground truth. So here is the ground truth. And here is a comparison to just training a NeRF model from scratch, so from a random initialization. And you can see that it converges. It takes more time to converge because the GRF is already seen a lot of objects and is leveraging that prior. And we can see also that, okay, here these are the same results, but with PSNR. And we can see that GRF is getting better results. Okay. So here we have some other results. So here they trained for longer than the previous experiment. And basically they say that GRF gets better quality than NeRF. So if you forget about converging faster or being able to handle fewer input views, here if we just focus on quality, GRF allows to get better quality than NeRF because GRF leverage again all the information it has seen in the past on all the information it has learned. So okay, that concludes this video. So that's a very interesting paper. It has a lot of implication. Either you can just use it to get better quality because you take advantage of all the information. You have all the scenes you've seen so far, all the data you've accumulated, or you can also use it to use either to converge faster if training time is an issue for you, or to use fewer views as inputs. Okay, so I hope this video was helpful to you. If you want me to implement the paper and release a video about it, let me know. If you like this video format, let me know as well. And see you in the next video.